you will soon see that the vanishing condition is going to be very helpful, in particular when we want to show that a series is not convergent. So, if we know that a series converges, then what can we say about the sequence of the terms an? It's a natural thing to ask. Well, the following theorem is going to give us a necessary condition for convergence. It tells me that if I know that my series is convergent, then the limit of the terms n has to go to 0. And that intuitively makes a lot of sense, right? If my terms don't become very, very small, there is no way that if I add infinitely many of them, I stay finite, right? Like if I'm adding something that is, vague-ish, infinitely many times, that would not end up being finite. So it makes sense that it has to be the case. And the proof is actually quite simple. So we're going to assume that my series is convergent, because if convergent, we know that the sequence of partial sums converges to a limit, let's say s. And now you see, Sn minus nn minus 1 is just an, right? So now the limit of the an is the limit of Sn minus 1. We can apply limit laws. So this is the limit of Sn minus the limit of Sn minus 1. But these two, they're just the same. Just one is like a subsequence of the other one. So they have the same limit. So this is s minus s, which is 0. And that completes the proof. Now, there is a huge warning attached to this theorem. The converse is not true. Repeat, the converse of this theorem is not true. If you know that the limit of the an's is equal to 0, you cannot conclude that the series is convergent. This is a very, very common mistake. Please, please, please do not make it. And I'll show you an example so you never forget that the converse is not true. So, you see, 1 over n goes to 0. 1 over n squared goes to 0. We saw that the harmonic series 1 over n diverges. We saw that the series of the 1 over n squares converges. So here we have two examples of sequences that go to 0, but that their series, one diverges and the other one converges. So when we know that the limit of the an's is equal to 0, we cannot conclude anything. It's pretty useless. So how do we use this theorem in practice? Well, what is actually useful from this theorem is the contrapositive. The contrapositive tells me that if I know that the limit is not 0, then the series is divergent. And here is an example. If I take a look at this series, and maybe I have no idea what to do, but then computing the limit of the term, the general term, is actually quite simple. So that's what I'm going to do. And I see that this goes to 1. 1 is different from 0. So immediately I know that my series is divergent. And here, when we say that the limit is not 0, means that either that the limit exists and it is not 0, or that the limit of the an's doesn't exist. So for example, if we consider this series here of minus 1 plus 1 minus 1 plus 1, we take the limit of the general n term of my series, and we know that that limit doesn't exist, and because the limit doesn't exist, in particular, it is not 0, so then my series diverges. And this is how we actually use this theorem. We use it just to show that a series diverges, but we cannot use it to show convergence. And I'll say it one more time. If we know that the limit of the an's is equal to 0, you cannot conclude anything about the convergence of the series, the an's. We saw that the harmonic series, which is given by sum from n equals 1 to n of 1 over n diverges, and that sum from n equals 1 to infinity of 1 over n squared converges. So the converse of that theorem is not true.